Okay, so as I said last week, the exam's open today and tomorrow. Get on any time. Set it 90 minutes to kind of complete it. I already talked a little bit about that. If I decide to change something, I'll let you know. But look at the keep an eye on the announcements, just in case. I don't know, an error comes up, for instance. I know that Safari has issues with it. So if for some reason, someone starts taking it and they realize that there's an issue and, it's some web browser I haven't thought of, I've kind of got the main ones. I'll kind of probably try to get something out there real quick so that you're aware of that. But I think, we should have all the kind of technical stuff covered. I posted some videos on the YouTube playlist. It's me working through every problem, kind of split up each one in half. So practice exam B, practice exam A. There should be me working through one of the, every problem at least one point in time in those videos. If you're kind of working through there and you get stuck on those, if you have any last minute questions, feel free to email me throughout the next kind of almost less than 48 hours now, but kind of the next 2 days. Anything else I can cover? Any other kind of just questions pertaining to the exam and taking it, not specific problems like, we'll kind of hit those next, but any questions about the exam that you want to clarify?
I think last time there was a bonus.
Yeah, so I usually don't say this ahead of time until it's kind of out there. But yeah, there actually are 18 questions. There is one bonus question. It's kind of titled bonus question. So initially, it'll look like everything's being scored out of 104, similar to the last one. I can't change that until everybody's completed it. And then I'll re-upload kind of what looks like a separate exam, but it's basically just taking your score and scoring it out of 100. Right? So any grade that you see when you initially take it, your grade can only get better, right? So because if you get an 80 out of 104, that's really an 80 out of 100. But until everyone's taken it, it's going to appear a little bit lower. Okay? Any other questions?
Will you be able to use Excel as a calculator?
Let me turn up I think my volume's a little bit too low for me to hear you. Say that one more time.
Will we be able to use Excel as a calculator on the test?
Yeah, you can use Excel similar to the last one if you want to use Excel. Even for the short answer portion, we didn't get as much time to cover how to do it in Excel with hypothesis testing. We did get a couple examples. If you're comfortable with that, feel free to do your short answer kind of work. I already told you that the short answer is a hypothesis testing question. So, that short answer you can do in Excel. You can do the work by hand, take a picture of it. If you want to type it all out, kind of the work that you're doing, you can type it out in Word. All three of those are fine options. As I said on Friday, just make sure you show as much work as possible. I want to be able to give as much partial credit there if you do get something wrong. Any other questions? Okay. So now we move on. Are there any questions that somebody wants to review from one of these practice exams? I can kind of start with those. Otherwise, I'll probably just kind of pick and choose and go through some things I think would be helpful going into the exam. No specific problems or? Okay. So I'm going to go through a little bit here first, just to kind of, I think, similar to the first exam, it's good to kind of have an idea about what all these equations are. And for these, we can really group them pretty easily, right? So you're kind of reminded here, and hopefully at this point we don't need to be reminded, but anytime you have kind of the standard deviation, that's just the square root of the variance. So if I give you the variance, if you take the square root, that'll give you the standard deviation. If I give you the standard deviation, well, that's just sigma. So if I want the variance, which is sigma squared, I just have to square it. So that's kind of a reminder there. These next set of equations, right? These are our uniform distribution equations. So I'll probably work quickly through a uniform example here. We'll be using these equations right here. You can kind of come down here. This is just kind of a reminder. When we're starting out originally with a data or a variable that's normally distributed, we can turn it into a z-score by simply subtracting the mean and dividing by the standard deviation. We can also work the inverse, right? Where if I give you the area you want in the tail, you can find what z-score that corresponds to, and then translate that into whatever the cutoff value for the original variable is. So this is kind of like way back when we were just looking at normally distributed variables, like when we looked at that birth data. We then said if we take a sample, right, this is what we did with the birth data, we know that the variance of my sample means is just the original variance divided by the sample size. Right? And if I want the standard deviation of my sample means, well, it's going to be that variance, but we have to take the square root of it. Right? That's going all the way back to just thinking about what's the distribution of my sample means. Right? That's kind of what these equations are. And then here we have, how do I think about the distribution of my sample proportions? Well, that variance of my sample proportions is calculated a little bit differently because I know that the variance for a proportion example is just p times 1 minus p. Okay? So that's kind of some of our older stuff. We come over here, I wouldn't worry too much about this other than if I'm looking at the distribution of my sample means, right, we said those top right equations, really what they're reflecting is, switch over the dot came here real quick, that if I want to think about, I know that the standard deviation of my sample means is the square root of the original variance of the data I sampled from over my sample size. So if I want to calculate a z-score for a sample mean, I'm going to take that sample mean. I know that the sample means are distributed normally around whatever the true population mean is. And then I want to divide by the standard deviation. Well, I can kind of do that all at one time, or I can calculate the intermediate step and then just plug that in. Right? That's kind of going back to when we're just looking at the distribution of sample means. The next set of equations we had, let the screen catch up to us here in class. Maybe. There you go. Is here's our confidence interval equations, and here's our test statistics for hypothesis testing. Now, remember, anytime we have a sample mean and we have a known population variance, sample mean, known population variance, we're going to be using that standard normal or the z-table. And this formula sheet kind of reminds you of that. If I have the population variance and I'm looking at a sample mean, I can build the confidence interval for the true population mean. I should be using that z-table, or that standard normal distribution. My test statistic is a z-statistic. It's coming from that standard normal distribution. Same thing's true about sample proportions. For the confidence intervals, right? We're still using the standard normal. And when we calculate the test statistic, it's still kind of coming from a standard normal distribution. The only time we need to use the student t distribution is if we're looking at a sample mean example, and all I have is the sample variance. So these equations remind me, if all I have is the sample variance, then for the sample mean, my test statistic comes from the student t distribution, and I need to use that student t distribution to kind of build my confidence interval. It's kind of breaking down this formula sheet so that you kind of have everything laid out. And if it helps, write that stuff next to it. Kind of want to go back through this and make sure that you've got ahead of time, have this formula sheet downloaded, maybe insert some comments or some text next to these things that identify what all these equations are. Okay? Any questions over anything on this formula sheet? I think it also has kind of a reminder of kind of if we have a greater than sign in the alternative hypothesis, it's a greater than or a right-tailed test, less than sign in the alternative hypothesis, less than or left-tailed, and then a not equal to sign, that's our two-tailed. And it kind of reminds you when you're finding the p-value, you got to find that area in the tail, but then remember, I've got two sides, so I need to multiply it by 2. Okay? So it really could be everything you need to know about the formula sheet, or at least kind of have a synopsis of what it is. So I said, I think I'm going to go back just because we haven't done this in a while, and I think these are like really easy points. Right? Hopefully these first 4 questions look similar to the first 4 questions on the exam that I posted. And I've written it already, it's up there, so I kind of know. So let's say we have this example where we're looking at the wait time for some roller coaster. It's between what, 15 and 75 minutes. So anytime I see this word uniformly distributed, right, this variable is uniformly distributed, I should be thinking about, I've really just got a rectangle, right? And it starts and stops at this minimum point. And if it kind of helps, the general kind of notation we were using was D is my maximum, C is my minimum. Right? We then said, okay, well, what's the height of this distribution? Well, if everything's equally as likely, it's just 1 over the range, or 1 over D minus C, 1 over max minus the min, right? That's the kind of length of this interval, is D, max minus the min. So the height is going to be 1 over that. So here we've got what? 1 over 75 minus 15 equals 1 over 60. Okay. That's just kind of thinking about for the next 4 questions, this is the setup I have. Helps to draw it out, I think. So if I want the mean of this distribution, well, the mean of this distribution is just going to be what splits this exactly in 2, right? The middle point between these 2 values. So if I want to find the mean, and if we look at our formula sheet, it's pretty intuitive, but it'll remind us. So here's our uniform distribution equations. The mean, you simply are finding the average of the minimum and the maximum, right? So 75 plus 15 over 2. So I think if we put that in our calculator, we should get 45. Okay. So all I did there was use that formula I had for the mean for a uniform distribution, or uniformly distributed variable, I should say. Oh, let me get rid of this. That's just plugging my values in here. My max plus my min divided by 2. If I wanted to find the variance of that equation, in fact, I think that's what number 2 asked for. Right? The variance, if we look at our formula sheet, will always follow this format. The maximum minus the minimum squared, d minus c squared, divided by 12. Okay? So, oops, there we go. So I'm just taking that formula that I looked up on the formula sheet. What was it? It was d minus c squared over 12. So 75 minus 15 squared over 12. Excuse me. I think, let's see what, 3, oops. I think this works out to be 300 if I remember correctly. Here, brought my calculator today so I can kind of check some of this stuff quick. No, I was way off. It is, what am I doing here? 60 squared divided by 12. Yeah, no, 300. Okay. So we've got, hopefully, if we can identify these are our uniform distribution equations, the mean and the variance should be relatively easy. All right, so we got a mean of 45. And we got a variance of 300. So the next question is, what's the probability that you wait in line for more than 50 minutes? So what we're thinking about here is, I'll use the red marker to kind of show, we've got what? Greater than 50? So we're thinking about this area, right? If I had to put 50, it'd be right there. Well, this is where knowing where the mean at is helpful, because what should the area to the right and the left of our mean be? Just 0.5, it splits it in half. So you can kind of see if I were to shade in this area to the right of my mean, it's going to be larger than the area I want. So I know that this has to be less than 0.5. So if I look at it right away, I know this is either C or D. Okay? This is not less than 0.5. A makes no sense. I'm looking for a probability. It has to be between 0 and 1. Right? The area under this curve, or like within this box here, is 1. So from here, if I had to guess, this is just kind of helpful hints. I mean, 50 is pretty close to that mean. So my area is probably going to be pretty close to 0.5, right? If I'm guessing here, I'm probably going to go D over C. But I can kind of calculate what it is. And the easiest way I think to think about this is, well, I have the area of a rectangle, right? Okay. So how do I find the area of a rectangle? Well, I just take the height, which is 1 over 60. Right? Calculated that up here. The length, it goes from 50 to 75, so 75 minus 50, or 25 over 60. I can enter this in my calculator. I don't have to do this intermediate step. And this should give me what? I think it's 0.42. Is that right? Let's double check. Yeah, it'll end up being that 0.42. Okay. Any questions on that before we finish this last one up? Okay. So I'll show you something a little different since you guys are here and kind of trying to do well in this exam. So number 4, it says, what's the probability it's between 30 and 45? Okay. So what we could do is, put 30, 45, shade the area in between. then it's kind of very similar to the one that we just did, right? I would, instead of having an interval of 25, I think 15 to 30, right? That's only 15. So it would end up being 15 times 1 over 60. Not too bad. Well, what if I had done something like this? This might be something that looks more similar to what I would do on the exam, right? So we've got our 15 to 75. We know the height is 1 over 60. So what if I maybe instead said, okay, what's the probability it's between 25 and 30, or between, I don't know, 50 and 55. So when I say that or, what I'm really thinking about is I want the probability I'm in this range or in this range. So if I can find the probability of each one, there's no overlap, there's no intersection, so I just need to add them up. Okay? So I use the same kind of thing. Well, what's the length of this interval? Well, 30 minus 25, where it has a length of 5, times 1 over 60. Right? So this will give me what? 5 over 60, approximately 0.083 repeated. So the area of this rectangle is 0.083. At this point, I don't really need to go back through, find the interval, because if I look at this, 50 to 55, it's an equally length interval. So what should the area here be as well? Same height. They're both an interval of length 5. So they're both going to have a probability of occurring of 0.083. So if I want to add these two together, it's really just 0.083 repeated plus 0.083 repeated. Or I can multiply that original area by 2, right? Either way should work. And I get about 0.1666 repeated, but if we round it at some level, it's going to be 0.1667. So if I give you two intervals of the same length, you really only have to find the area of one of them, and you automatically know the other area is going to be exactly the same. Now, I kind of think it's easier to think about this as the height and the width of a rectangle. If you really want to, if we look at our formula sheet, you can use this. What's your, the beginning and the end of your interval. So for example, ours was in that last one, 30 to 25, right? And then divided by the maximum minus the min, so 75 over 15. And it would give you the same answer. I just think that the visual of drawing the distribution out, thinking about it as height times width or length to find the area of your rectangle, probably a little bit easier. Okay? You're getting too lost in the formula there. Any questions on that one? And I point out in all of these, it's very helpful to do things like we were doing when I said, okay, what did this area have to be less than? Well, the area, it's going to be smaller than that area to the right of the mean, so I know it has to be less than 0.5. Doing things like that can really help you rule out some obviously incorrect answers or from making some really, easy mistakes, okay? Like forgetting to subtract from 1 or, something like that as we work through some of these other examples. Okay. Oh, and we were working off of practice exam B. I should have mentioned that ahead of time. I apologize. All right, we're looking at practice exam B here. Okay. So I changed this one because I know what the one on the exam looks like. So the one I just worked through might be a good one to kind of think about there. I want to do what's productive for everyone. So would you rather work through some hypothesis testing stuff or kind of going back and doing some old, like if I sampled, what are the distribution of my sample means and the probability of seeing a sample mean above a certain value? Any preferences? Anyone on the Zoom, any preferences? All right. I'll work through some of these because I think we haven't seen those. We did a lot of hypothesis testing towards the end of last week. So let's say I've got this random variable x, and it's the amount of what? Rent, the average Indiana college student spends. So we've got, and I think this is probably dated, but we've got a mean of $460 and a variance of 10,000. Okay, so I've got that kind of written out. It's this normally distributed variable. We know it's mean, we know it's variance. What's the probability that the rent for any one student is going to be greater than 600, or the probability that x is greater than or equal to 600? Well, right away, I think as you're working through this exam, start drawing things out all the time. It really is going to help you kind of narrow down what the possible answers could be. So on this one, I know that I've got this variable x. It's normally distributed, and its mean is what, 460? And I want the probability that it's greater than or equal to 600. So right away, what do I know this probability has to be less than? What's the area to the left and the right of the mean? All right, the area to the right of the mean here is 0.5. So the area I'm looking for is something smaller than that. So right away, I can rule out A and B, right? Automatically, I can rule A and B out, right? Now from there, what do we want to do? Well, we've got a normal distribution. We need to convert that into a standard normal distribution so we can use our table. So I want to turn this into a standard normal distribution. I know that the z-score for my mean should always be 0, just to kind of help me think about this. And the z-score for 600, right? And I'll show you where we find this in our formula sheet, but we simply take the value for x, subtract the mean, and divide by the standard deviation. Okay? Now, I believe we were told that the original variance was, what, 10, I think it was 10,000. So the standard deviation would just be the square root of that, right? Or if I'm thinking about this correct, should be 100. Right? So now that I've got my standard deviation, makes this a little bit easier because I'm interested in the x value of 600, mean is 460, and now my standard deviation, now my standard deviation is 100. I'm just plugging my values in. And I get about 1.6. Now I can go to the table. Now the table will tell me the area to the left. So this is where it helps to remember. We know this probability we said is going to be less than 0.5. So when I go to the table and look this area up, it's going to tell me the area to the left of 1.6. That'll be something greater than 1.5. I then have one more step, which is that I'll have to subtract it from 1 to get the area to the right. So I go to my table. I look up that z-score, so standard normal table. I've got a z-score of positive 1.6. So I'm going to scroll down here. 1.60, so 0.9452. Right. So the area to the left here, 0.9542. I wanted the area to the right, so I'll subtract that from 1. So 0.0408. Actually, is that was it 9542 or 9592? Can't even. It was 4. Couldn't even read my own writing. So this is going to be what? 0.0458. Oops, sorry.
1.4.
Yep. Thank you for saying that. I did bad math in my head, right? This is 140 divided by, sorry about that. Yeah. So you're going to do better on the exam than I would. So I've got 1.4 here. We don't look up 1.6, we look up 1.4. So we're going to have what? 0.9192, okay? Sorry about that, yeah. 0.9192, which is going to change our answer a little bit. Do what, 0.0808? I'm looking at this correct? Right. Yeah, sorry, instead of 1.6, that should have been 1.4. But the procedure of how you go through this would look exactly the same, right? So we end up, practice exam B, yeah, 0.0808, okay? But, really, as soon as I drew that one, I could have eliminated A and B right away. I'm down to a 50-50 shot. Okay? So what if I wanted instead the probability that it's less than 400 or greater than 520, right? So once again, it probably helps to just draw this out, and I'll kind of zoom in on it here in a second. So actually, sorry, this is our variable x. It's centered around 460. And I want the probability what? Greater than 520 or less than 400. So I'm looking for something like this. Okay. Now, if I look at this, And I think about that z-score equation I have, which was take the x value you're interested in, subtract the mean, divide by the standard deviation. We already had the standard deviation before as 100, so that kind of helps us already. We're a little bit less work than the last one. So if I want to turn 400 into a z-score, so 400 minus 460 over 100, negative 0.6. But notice, how far away from the mean is 400? 60. How far away from the mean is 520? 60. So I know that if I've converted, let me see if I can get this all on one line here. When I convert these values into z-scores, if 400 has a z-score of negative 0.6, well, 520 is the same distance above the mean, so it's going to have the same z-score, but positive. So I've kind of turned this one into making it easier to even think about, we've been talking a lot about hypothesis testing, and this is kind of similar to like a two-tailed test. I mean, it's not a two-tailed test, but it's similar in how we would find this, because the area to the left of negative 0.6, I'll go to my table. I look up negative 0.6, negative 0.60, right? It's the second decimal zero, so 0.2743. So the area to the left here is 0.2743. Well, I know I have an exact, from the same size tail over here. And now it's just a matter of adding these two together. So it's going to be what? About approximately, we add those together, 0.5486, if I'm doing the math in my head correct there. Okay. So I'll usually do something like this where I give you two values that are like the same distance away. So it's a little bit easier. Like once I have this test statistic, I really didn't have to go, or test statistic, sorry, z-score. I didn't have to go through all the steps to find the second one. So that made it a little bit easier. Okay. Any questions on that before I keep moving? Okay. So what if I then take a sample of 25 students from that original normally distributed variable, right, which was rental expenditures? What would the mean and the variance of my sample means be? Well, this is where if we look at the formula sheet, so first of all, when we were using that z-score equation, when we just had a normally distributed variable, that guy right here, right? Converting those values for x into z-scores. When I'm looking at the distribution of my sample means, well, my sample mean should always be normally distributed around the mean of the original data I sampled from. And they'll have a standard deviation, which is not what I wanted to find. The question actually asks for the variance. So they'll have a variance of those sample means will be the variance of the original data I sampled from divided by my sample size. Okay? So in this problem, right, if I'm sampling from that original variable that had a mean of 460, well, then my sample means, as long as, will always, as long as the original variable was normally distributed, or I have a sample size over 30, which here the original variable was normally distributed. The mean of my sample means will just be that original population mean. Okay. Now the standard deviation, or actually here we wanted the variance of my sample mean, sorry, was the original variance over my sample size. So that was what, 10 million over 25, or 10 million, 10,000 divided by 25, which should give us 400. Right. So now this allows us to think about, okay, we've got a variance for this distribution of sample means of 400, and the mean is 460, right? The original mean, and then the variance we just divide by the sample size. Now, if I wanted the square root of my, if I wanted the standard deviation of my sample means, all I would have had to do, right, is take the square root of the variance, right? Square root of 400. So sometimes I'll ask you for the variance on a question like this. Sometimes I'll ask you for the standard deviation. So make sure you're reading it carefully. But kind of the key there is the mean is just the original mean of the data you sampled from. And the variance is just the original variance divided by the sample size. Okay? Any questions on that one? Because this is going to be a pretty important problem on the exam that you know how to find this. Because like on 8 and 9, you're going to have to use this information. And there's no way I can truly kind of make this one not be cascading. Okay? So it's really important that you know you can identify the mean and that standard deviation or the variance of the sample means. So on this one, I only had one following question, but I could have two on the exam. So what is the probability that the sample mean is greater than 475, but less than 500? Okay. This one has a little bit of extra work. It might even be not quite this mean in the exam. So I've got my distribution of my sample means now. So what I want is the probability between what, 475 and 500. So right away, what do I know this area has to be less than? 0.5, right? Because the area to the right of the mean is 0.5. I want an area smaller than that. I know it has to be A or B, right? So I'm making these multiple choice exams. As long as you can draw this out, you can really make this a lot easier than having 4 options, okay? So I'm going to think about what do I want to do here? I need to take this normal distribution and I need to convert it into z-scores. Okay? So I'm going to take that value of 475, turn it into a z-score. How do I do that? Well, if we want to find the z-score and we're looking at the distribution of our sample means, it's take that sample mean, subtract the population mean. And what we really want to do here is divide by the standard deviation of my sample means. So this will look very similar to when we're calculating z-statistics, right? The only difference is we're not using assumed true mean. Here's an example where we have the actual mean. So this equation was the square root of the original variance over my sample size. Now, I already really kind of have that intermediate value calculated. It's a square root of 400 up here. So I could just plug that into my denominator. So what, 475 minus that mean of 460 divided by, and I could have written these numbers in here, or since I already know it, it's just the square root of 400. So if I do that, what do I get? Looks like 1.25. So 1.25 here. Then I can do the same thing for the value of 500. The only thing that would change in this equation is I'm now looking at the cutoff value, not 475, but 500. Okay? So if I put 500 in there instead, I'm guessing it is 2.5. Yeah. I'll get 2.5, right? And I wanted the area in between. Okay? So what I'm going to first do is look up the area to the left of 1.25. And then we're going to look up the area to the left of 2.5. If I subtract that blue area from the red area, I'm kind of just left with what's in between, which is what I originally wanted, right? So anytime I want to find the probability of being in between two values, I find the area to the left of each value and then subtract the smaller area from the larger area. So I'm going to go to my table, look up 1.25. So scroll down here, 1.25. So 0.8944. So here we got this blue area. What did I say? 0.8944. That's kind of that blue area. Then if I look up 2.5, so scroll down here, 2.50, right, the first column, 0.9938. So 0.9938. Right? Now that I have the red area and the blue area, just subtract the smaller from the larger. Wait, did I not look this up right? Hold on. Why doesn't this number look right? Greater than 475, but less than 500. What did I do wrong here? Oh, because hold on. This is why I need to not do math in my head. Anybody who was working along, this is wrong. Sorry. So I was using the mean of 450. It's 460. So 475 minus that. Okay. So this was not 1.25. I'm sorry. This is 0.75, which would then make the other one 2. So sorry, instead of 1.25 and 2.5, it was 0.75 and 2. Now I go through the same process, right? I look up 0.75, 0.7734 was the area to the left there. So 0.7734. And if I look up that z-score of 2, 2.00, 0.9772. So this was 0.9772. Now I'll subtract the smaller from the larger one. I'm going to get what? Whatever the 0.2038, right? If I do that math. So subtract that smaller one from the larger one, and I'll get 0.2038. Right? Sorry about that. I was thinking that the mean was 450 when I was entering it in my calculator here. Any questions on that one, since I kind of botched a little bit there? Okay. Yeah, so when you're doing this, what I just try to do is do some of the math in my head before I enter in my calculator. It's kind of a good check. You know, just try to get this all entered into your calculator so that you're not kind of even looking at these numbers, like mixing anything up there. I looked at that and saw 450 instead of 460 for some reason. Okay. You know, and this is a good example of like, so on the short answer, if you write all this out, like if I had all this and I had made that mistake and I say it's equal to 1.25, I'm only going to take like either, depending on the problem, at 1 point or half a point off, because you have everything set up correctly. You would have looked at, and I'm not going to then I'm going to use this and assume that this was true. After that point, you did everything right. So I'm only going to take a small point or half point off for the computation, right? So this kind of, I guess my mistake is good for you, in that it heightens its, the importance of showing me all your work. Okay. All right, so that kind of gets us through those. We've got 12 minutes left. I want to work through some student T stuff, so we're going to go down here to problem 15. Okay. So this information is used for the next 5 questions. So even though we're skipping over 14, I want to kind of work through a problem. This is more of a, how do we identify what distribution we're using? I kind of went over that on Friday. I'll go over that one more time at the very end of class. So we've got a, what? Oh no, this is, we have a known population set. Do I have one here? I'm gonna have to switch exams. Let me see. We go to practice exam A instead. Here's one. Okay, this is what I want to make sure we work through. Okay. So here, I've got kind of a survey of 30 dentists. I find a sample mean of 145,000, and all I have is a sample standard deviation. I don't know the true population mean or variance. So I've only got a sample standard deviation, so I should be using the student T distribution. Automatically, I should be thinking student T. So if I want to build a 90% confidence interval, I'm going to go to my formula sheet and look and say, okay, I've got a confidence interval using a sample mean, but I only have the sample variance, so I should be using this guy right here, right, this equation. So I'm just going to have this pulled up. If I'm taking the exam, I'm going to have this pulled up. I'm going to look at my values and just start plugging them in, right? So I've got this formula down. If it helps me to, I can just write it down. You don't have to look at the formula. I guess I could technically write down my own. So we had the sample mean plus or minus that t value that gave me alpha over 2. And here, right, this kind of guy represented the standard deviation of my sample mean. So I could break this down into steps if I wanted to, or just plug everything in here. So the sample mean I found, if I remember correctly, was 145,000. I haven't looked up this t-value yet. The sample variance, well, if I go back to practice exam A, the sample variance, I wasn't told. I know the sample standard deviation, okay? So here, I need to put in S squared. All I have is S, right? I just have the standard deviation. So I'm going to take, what, 10,000 and square it, and then divide it by my sample size of 30. Now I need to find these t-values. I want the 90% confidence interval, so what should my alpha be? Remember, alpha is the area outside the confidence interval, but I've got half of alpha on each side. So here, if I've got a 90% confidence interval, my alpha is 0.1, but I only have 0.1 divided by 2, or 0.05 on either side of my confidence interval. So I know the area I want in the tail, so 0.05. I'm going to go to my student t distribution, but I forgot, okay, I know I want 0.05 in the tail, but what's my degrees of freedom? Well, degrees of freedom is simply n minus 1. So here my degrees of freedom is what? 30 minus 1, or 29. Okay. So I'm going to scroll down, area of 0.05, degrees of freedom, 29, 1.699, right? So I plug in that 1.699. Well, now I get everything I need. I add my margin of error to my upper bound, and I subtract to get the lower bound. Now, one thing on these when you're finding confidence intervals, notice like none of the lower bounds are the same. So once you calculate the lower bound, you automatically know which answer it's going to be. I don't give kind of multiple where you have the same lower bound, so you have to actually go then and calculate the upper bound. Once you have one of them, you should be able to identify which of these is the correct answer. Okay. Any questions on this one? Yeah. Right, so this is where, if I go back to my formula sheet, it reminds me as well. So I want to find the t-value. It gives me alpha over 2, or 0.05 in our case, right? Alpha was 0.1. So 0.05 in the tail, and our degrees of freedom is n minus 1. Well, my sample size n was 30, so my degrees of freedom was 29. So when I go to that student t table, I want 0.05 in the tail, and my degrees of freedom is 29. And that's how I find that value. Yep. Any other questions on that one? All right, so I don't know what this works out to be for the sake of kind of us working through some stuff at the end here. You've got the answer key, so you can kind of look up. But I just showed you how you can basically get to the point where all it is getting this entered into a calculator or into Excel if you want to use it as a calculator. Okay. So suppose the U.S. News publishes an article that says the average dental salary is $150,000. You think that you want to test for whether or not it's less than that amount. What would the null and alternative hypothesis be? Well, anything I want to test for is my alternative hypothesis, right? So I want to test to see, is it less than 150,000, net population mean? So I assume the opposite is true, which is that it's greater than or equal to that 150,000. Okay. So I've got a less than sign in my alternative hypothesis. So I've got a left-tailed test. I'm looking at that student t distribution. All right. So if I'm thinking about my critical values, for a left-tailed test, my critical value should be what? Well, remember, the student t distribution, just like the standard normal, is centered around 0. So if I'm wanting really small areas in my left tail, like alpha 0.01 and 0.05, my critical value should be negative for a left tail test. Remember, negative critical values for a left tail test, positive for a right tail test, pairs of critical values for a two tail test. Okay. So we identified the null alternative here, right? We already got that. Our critical values, if I look here, well, I know it's going to be A or C because I know they should be negative. Now, if I want alphas of 0.1, 0.05, and 0.01 in that lower left tail, my degrees of freedom is still same thing as when we did the confidence intervals, 29. So I'll go to my student t table and say, well, look, the areas I want in the tail are 0.1, 0.05, and 0.01. So I want these three columns. I then go down to 29 degrees of freedom. Whoops. So it's going to be 1.311, 1.699, and 2.462. Those will be my three critical values for those alphas. Now, remember, the student t-table always looks at the right side of the distribution. I've got a left-tailed test, so it's going to be those three values, but negative, right? So those three values, but negative. Okay. Any questions on kind of finding those? Okay. Now, if I wanted to find my test statistic, all right? If I go to my formula sheet, it kind of reminds me, you have a sample mean and only a sample variance, right? So here's your test statistic. It comes from a student t distribution. I mean, to find the test statistic, it's really just a matter of getting our values plugged in. That sample mean we found was what? 160,000? No. What was it? 145,000 maybe? 150,000 was the value we had in this null hypothesis, and the sample mean we found was 145. Yep. So 145,000 minus that assumed true mean of 150,000, and then divided by, and this is where we could have calculated this standard deviation of my sample means ahead of time. It was going to be the square root of my variance, which was 10,000 squared, right? Because I had the standard deviation was 10,000 divided by 30. Okay. So this should give me my test statistic. Now, if I'm thinking about this, the distribution of my sample means, well, I've assumed that population mean is 150,000. I found a sample mean of 145,000. So if I'm thinking about the area in the left tail here, right, that's going to represent my p-value. But if I'm trying to convert this into a t-score, well, I'm below the assumed true mean, so I know my test statistic should be a negative value as well, okay? Because I'm going to be a certain number of standard deviations below the assumed true mean. Now, if I'm guessing here and I look, well, I can rule out C and D because those are positive. B, a test statistic of negative 273 seems outrageous. It's theoretically possible that this could be negative 273, but if I'm going to guess, I'm probably going to go with a more reasonable test statistic of negative 2.74. Let me double check. Yeah, so sure enough, if we do calculate it, we end up getting negative 2.74 if we round to the second decimal. Okay, so I get this entered into my calculator, I should get negative 2.74. So we're running out a little bit of time here. But if I then wanted to make a rejection decision here, I would plot these critical values, draw areas. Once I have those critical values plotted, draw arrows into that left tail that represents my rejection region. I'm then going to take that test statistic of negative 2.74, plot that against my critical values, and determine whether or not I reject or fail to reject. Right? If it's in that rejection region, I reject. If my test statistic is somewhere out here, I would fail to reject. Okay? So I said I'd go over one more time. We've got about a minute. Just as a reminder, if you have a sample mean and you know the population variance, or you're dealing with a sample proportion, you can use the z-tables there. Okay? If I'm looking at a sample mean and I only have a sample variance or sample standard deviation, that's the only time I use that student t distribution. Okay? All right, so hopefully that gave us kind of a refresher on some old stuff, a little bit of hypothesis testing. Like I said, those videos are up there of me working through all the other problems. If you have any other questions kind of before you take the exam, make sure you reach out. Other than that, we'll kind of then start up on new material once we meet again on Wednesday, okay? All right, we'll see you guys on Wednesday. Good luck on the exam. And feel free to reach out if you do have questions.